All right. Hey, everybody. So in this video, I want to explore a new kind of surface. Last video, we looked at developable surfaces, which had our Gauss curvature equivalently equal to 0. And today, I want to look at the surfaces that have mean curvature equivalently 0. And these surfaces are the so-called minimal surfaces. So let's take a look at them. So as a reminder, our mean curvature is literally going to be the average of our two principal curvatures. So at any point on our surface, we can calculate different measurements of curvature, of normal curvature, and we can calculate the two principal curvatures, kappa 1 and kappa 2. At that point, we can take the average of these to get our mean curvature, which we denote with a capital H. And so a minimal surface is going to be a surface that is parametrized in such a way that the mean curvature is equal to 0 everywhere and at every point. It turns out we have already seen a handful of minimal surfaces in this class or in this video lesson series. Two immediate examples are the plane and the helicoid. And so I won't explicitly compute those parameterizations or their mean curvatures here, but I'll simply state that, right, the plane was our perfectly flat surface, right? It has all curvature measurements equal to 0, and therefore the average curvature equals 0, right? Kappa 1 and kappa 2 are themselves both 0. And at the same time, I should say, on the other hand, the helicoid is a non-trivial surface, right? So it does curve in space, it has curvature, but it curves in such a way that kappa 1 and kappa 2 are always in perfect balance with each other, right? Whatever kappa 1 is, kappa 2 is negative that. And so our helicoid, right, that was our surface that spiraled up like a helix, right? So it was like the surface version of a helix. It is parametrized in such a way, or it is defined in such a way, that kappa 1 and kappa 2 perfectly cancel each other out, and the mean curvature turns out to be 0. So that's our definition of a minimal surface. Notice that it's a condition on the mean curvature, but its name implies something about being minimal in a certain sense. And indeed, that's kind of true. An idea here that we want to explore is that minimal surfaces often have locally minimal surface area. And what I mean by that is that if I take a minimal surface like the plane, that will have as little surface area as it can locally. And if I sort of changed the surface in a local manner, so if I added like a little bit of like bumps to it or something like that, right? If I changed the surface slightly, that would necessarily increase my surface area as opposed to decrease my surface area. So small local changes in the surface will result in additional surface area. At minimum, at minimum, these surfaces we will see will become critical points for a certain surface area function, a function that measures the surface area and measures how the surface area changes as we introduce these little wiggles or deformations or variations in our surface. So to make that a little more mathematically precise, we are going to define the idea of a normal variation. So specifically, let's get this set up. So we're going to take a parametrized surface, or a coordinate neighborhood of a regular surface. We are going to take a subset of our domain. So if our original domain was U, let's take a subset of that, call it D prime. Let's make sure it's compact and connected, and let's let D be the image of that set. So here's our setup then. So we have got, yes. So we've got our usual function. So this is my x. This might be my area U. And that might be mapping to some sort of surface here, right? Not necessarily a minimal surface. This could be any surface. What I'm going to do then is I'm going to define a subset of this. So maybe my D prime will be this region here. That's my D prime. right? And when I map over here, I'm going to get a certain subset of my surface over here, which I will call D. So that's the image of my D prime. So I have a certain region over here, it's compact, it's connected, and this is its image over here. Furthermore, let's take a differentiable function defined on D prime, right? So I'm going to let lowercase h, not uppercase, but lowercase h, be a differentiable function whose domain is this. So that's just a multivariable calculus 3 function. Notice it's not a parameterization, it's not mapping into R3, it's just mapping into R1. Then a normal variation of my original surface x is a family of surfaces, a time-dependent family of surfaces, x sub t, or x superscript t, such that x superscript t is defined in this manner, which I'll talk about in just a moment. So this is a time-dependent family of surfaces. That means that my surfaces, right, are dependent on time, and every slice of time, every t, is going to be giving me a new surface. The way that those surfaces are defined is they're defined so that at time t, I had my original surface, right? That was my x that was originally defined, plus t times my function little h times the normal vector capital N. So in other words, I can take this image here, I can measure the normal vector, so my n, at each of these points, and maybe this is my normal vector, and I can measure my variation h, which might be bigger in some places and smaller in other places. And as I go forward in time, my surface is going to deform in that normal direction according to this variation function h. So if I go just a little bit forward in time, I won't have this surface anymore, but I might instead have this surface, right? And that might have bulged out a little bit or something like that. As long as my t values are relatively close to 0, this will be a well-defined surface that is still a nice parameterizable surface. And so I can talk about it as its own surface. Right? At time 0 specifically, this x superscript t is just an x superscript 0, which is just x. Right? Let me go back and say at time 0, this piece doesn't exist, and all I have is my original surface x. But for small values of t, right, this will slightly deform my surface, and as a result, I will get a new parameterized surface, a slightly varied version of my original, and all of my measurements will be slightly different and time dependent. So we can ask ourselves, how do our different measurements change? And in particular, because I'm talking about minimal surfaces and hinting about area, at time 0, our area is computed like this. It's an integral over d prime, and it was just the square root of the determinant of the first fundamental form. This is what we learned back when we were looking at the first fundamental form. At time t, we can compute the surface area of the surface just like we did at time 0. We take a double integral over d prime, and we take the square root of the determinant of the first fundamental form. But this is the first fundamental form of this new, slightly varied surface, right? It will be different and it will be time dependent. What that means is that I can actually make surface area a function of time, right? I can say that my a of t is this integral. This is measuring the surface area of my varied surface, of my variation surface at time t. So at time 0, it's just the area of the original surface. At time t, it's the area of this slightly deformed surface. And we can ask the question, how does this variation, this little h, affect the area? Can I always calculate a of t? And can I calculate a prime of t? Right? That will describe how the area is changing with respect to time. And in particular, if my surface that I was originally looking at was a minimal surface and it somehow had locally minimal surface area, that should imply that at time 0, my area was a local minimum. So what will that tell me about A prime of 0? So that's what we're going to explore now. So the first thing we have to do is compute our first fundamental form for our varied surfaces. So our original surface was x superscript t as a function of u and v. And that was just the original x of uv plus t times h times n. And I've rewritten it down here just without the u's and v's to make it look a little cleaner. Now, to calculate the first fundamental form, I have to take the first derivatives and all of their successive dot products. So here's x sub u and here's x sub v for my time-dependent parameterizations. Notice that when I take that partial derivative, so here's my partial u derivative, the end result has 3 terms. I'm taking the u derivative of x, gives me x sub u, and then over here, the t is just a t, but h and n both themselves depend on u and depend on v. So there's a product rule happening over here. So when I take the u derivative, the end result is h sub u times n plus h times n sub u. That's just the product rule in action. The derivative of the first times the second plus the derivative of the second times the first. The same thing is happening with x sub v. So with that in mind, right, our partial derivatives each have 3 terms. And when it comes time to calculate my first fundamental form, I'll end up with a number of different terms, right? Specifically, I guess I'll group them a little bit to make it easier, but if I didn't, I would have 9 terms, right? Let's calculate G11, that first entry, and see what happens. So the G11 entry is going to be just x sub u dotted with x sub u. But of course, this is x sub u of t, so it's really this whole thing dotted with this whole thing. And the end result is this line up here. Now, in order to calculate that dot product, I'm going to have to multiply in each and every one of these terms, right? Because the dot product distributes linearly. So what I get is, I'm going to get x sub u dotted with x sub u. I'm going to get 2 copies of x sub u dotted with the second term, right? So that's t times h sub u times x sub u times n. That's this one and also this one. And I will end up with 2 copies of, let's see, what's this? This is going to be my first term dotted with my third term. So that's x sub u times t h n sub u. And that's written here. 2 copies of that as well. All right, finally, what else? So we've done this one times this one times this one. We also need to do t squared times hu squared times n dot n. All right, so that's this middle term times that middle term again. We will need to do these last 2 terms. Right, so that's th n sub u times th n sub u. That's this term here. And we also need, I realize it's not actually written here, so we should add that, at least for the moment. We also need the term that comes from taking the middle term and multiplying it by the final term. So that's a 2. We're going to get 2 of those. T squared, and then it's h times h sub u times n dotted with n sub u. Okay, so that's great. So we got those terms in there as well. It turns out that term and several other terms will simplify nicely, but it's good to make sure we didn't forget it. Now, let's simplify all of this as much as we can. The very first thing I'll do, I just added this nice term. I'm going to mark that out. It turns out that we do not need that. This term will be 0. The reason being, our normal vector always has length 1, n has length 1, and as a result, n dotted with a derivative of n will always equal 0. Right? So n dotted with the derivative of n equals 0, and that term is gone. Similarly, n dotted with x sub u will also disappear, right? X sub u is tangent to our surface, n is normal to our surface. That will be a 0. What else we got? N dotted with n will just equal 1 because n has unit length. So that will just become a 1. And our x sub u dotted with x sub u is just another way to write G11, that first element of our first fundamental form in the original surface, the one that's not time dependent. So we're calculating G11 of t, but in reality, this is just our G11 of 0. So we've simplified it down almost as much as we can. There's one more thing we can do, and that's a little subtle. I want to take this term and rewrite it. This term turns out to be equal to -2 times t times h times x u u dotted with n. Let's move us over just a little bit further. Yeah, so that becomes -2 t h x u u dotted with n. And now why is that? Right? Well, that is really coming from the fact that if we take x sub u and dot it with n, it equals 0. Sorry, we'll just come up here, right? So this is coming from that if we take x sub u, dot it with n, we said already this expression just equals 0. But then, something that we did back when we introduced the second fundamental form, we took this observation and we took the derivative of it. Specifically, we took another partial u derivative of both sides of the equation, and the end result, this is an x u u dotted with n plus an x u dotted with nu equals 0. Right, so we took that clever observation, we took the derivative, the partial u derivative of both sides of that equation. We got this plus this equals 0. So xu dotted with nu is equal to negative xuu dotted with n. And that expression is exactly how we defined our second fundamental form, L11. So not only can I rewrite this in this form, but I can rewrite it even further by replacing this piece with L11. And now we are in a position, let's bring this back where I can see everything. Yeah, we're in a position to rewrite that entire first entry in our second fundamental form. So the G11 entry, I'm sorry, this is our first fundamental form. The G11 entry for our time-dependent normal variation is G11 minus 2THL11, right? That was this piece here that we were just talking through, plus a t squared times h sub u squared times 1, plus a t squared times h squared times nu dotted with nu. And there are similar computations we can do for our other entries as well. So the G12, the G21, and the G22 entries of our first fundamental form. Let's see what we get. And I'm going to group this in sort of a clever way that will serve our purposes. I'm going to highlight this, I'm going to group things according to t. So there's going to be a term with no t's, a term with a single t, and a term with t squared. And notice our term with no t is this one, the first fundamental form. A term with a single t involves the second fundamental form, and everything else over here involves t squareds. So if I go to write my first fundamental form, I get something like this. And I'm going to sort of ignore, more or less, the pieces with the t squareds on them. So I calculated a similar expression for all 4 of my entries. I have things involving no t's, 1t, or a t squared. And now I want to compute the determinant of my first fundamental form, because my end goal is to calculate area. And to calculate area, I need to integrate the square root of that determinant. So this is my time to calculate the determinant, let's do that. So when I go to calculate this multiplication here, what I'm going to see is that I will get certain entries that have no t's on them, and certain entries that have one t, and everything else will have more t's on it. So for example, when I'm multiplying through here, I'm going to get a g11 times a g22. Right, that will have no t's on it. I will get a negative 2t squared, I'm sorry, I'll get a negative 2th L22 times G11. What else will I get? I'll get a negative 2th G22 times L11. And everything else will have a lot of t's on it, right? Even if I multiply this term by this term, I'll end up with at least a t squared in there. So for the moment, I'm going to ignore that. That will be just a, plus t squared times a bunch of stuff. When I go to do the minus direction, it'll be the same thing. I'll end up with a minus g12 times g21. I'll end up with this 2th L12 times G21. And because this is a minus, a negative, that would become a plus. And then another plus, the other term, 2th G12 L21. And everything else will, again, just have too many t's on it. We'll end up with plus t squared times a bunch of stuff. And that stuff is all very real, right? It exists. But when I'm trying to take a t derivative of something, my t squareds aren't things that I'll care as much about. And we'll see this here in a moment. So going forward, the determinant I just computed could be summarized like this. I've got this piece, right? This is just the determinant of my original Gij, my original first fundamental form. Then I've got all of these pieces here, which can be described as follows. So I've got my determinant of my original Gij, and then these other pieces can be grouped as follows. We get a negative t times 2h times this sort of intermingling of the first and second fundamental form, right? So all that stuff, plus a t squared times something that I'm just calling r tilde, right? This is t squared times some remainder term, a bunch of stuff I'm not going to worry too much about. What I'm going to claim now is I can actually rewrite this in the following really slick way. I can factor the determinant of Gij out of everything. So I'd factor the determinant of Gij out of this first piece, and I just get the number 1. I can factor the determinant of Gij out of this piece by recognizing that h, my mean curvature, had this nice expression in it. This is something we talked about back when we discussed mean curvature. H can be written as 1/2 times exactly this thing divided by the determinant of Gij. So I can factor out a determinant of Gij, introduce this extra factor of 2 to counteract this 1/2, and replace that expression with a negative 4 th times capital H, the mean curvature. Finally, my remainder, I can factor out a determinant of Gij. It just changes that remainder by some amount. And so the end result is that my time-dependent determinant is the determinant of Gij times all of this. And so when I go to calculate the area at time t, I'm calculating the square root of that determinant and the integral of that. And that just becomes the integral of the square root of this piece times the square root of the original determinant times integrated du dv. So with that observation, we are actually ready to prove what we've been setting out to do, which is to find a relationship between mean curvature zero surfaces and this idea of area and being a critical point for area. And it's summarized in this nice proposition. A minimal surface, that is a surface with mean curvature zero, will be a critical point for the area function, meaning that if I take that area function, take its derivative, and look at it at time zero, that derivative will equal zero for any normal variation little h. So no matter what my normal variation function little h was, this will be true. Likewise, any such critical point, so any surface that satisfies this for any normal variation, must actually be a minimal surface and must have mean curvature zero. So these two kinds of ideas are not interchangeable, but they are one and the same. Let's see a proof, and we have to prove this in both directions. First, let's show that a minimal surface actually is a critical point. To see this, we're going to take a normal variation, a little h, and calculate our a of t. And from our previous work, a of t will equal all of this. That means that when I go to calculate a prime, I'm calculating the t derivative of all of this, and I can move that t derivative into the integral and calculate the t derivative of the integrand, so the t derivative of this, and then integrate up the result. So what I get is I'm taking the t derivative of what amounts to the t derivative of this piece right here, right? Which by the chain rule is just going to be this piece right here. And notice what we get. We're going to get the 1/2 out front, we'll get this square root in the denominator, and then times, this is all in the numerator, the t derivative of what was inside the square root. So that becomes, the 1 disappears, the negative 4thh becomes just a negative 4hh, and everything with a t squared on it still has a t attached to it, right? We got 2t times r plus t squared times the t derivative of r, but all of those things still have t's involved. It was only this first order term whose t disappeared. Now, a prime of t is equal to the integral of this ugly bunch of nonsense. But a prime of 0 is what we're really interested in. What is the rate of change of area at that initial time at our minimal surface? Well, at our minimal surface, we have this denominator just becomes a 1. These ugly, messy things involving r's all disappear because t equals 0 at this moment. And so what we get is just 1/2 times negative 4 little h big H times this square root of this determinant and all integrated up. And that will equal 0 regardless of what little h is, because we're at a minimal surface and big H will definitely still equal 0. Therefore, if we're looking at a minimal surface where our capital H is already known to be 0, this surface will be a critical point for area regardless of what our variation little h is. All right, now we have to prove the reverse direction too. So we have to show that a critical point for any h, little h, will in fact still be a minimal surface. So to see this, let's assume that a prime of 0 is equal to 0 for every h. That means, and then our goal is to show that capital H equals 0. The trick to doing this, very slick, is to just say if this is true for every little h, let's assign little h to actually equal capital H. So if this is true for every little h, then it should be true for little h equal to big H. And so if this must be true for every little h, then that must be true specifically in the case where this is equal to big H. And so what we have is that this integral must equal 0. And yet, the determinant of Gij will always be positive, so this piece is always positive, the negative 2 out front is always negative, and so the only way for this thing to actually be 0 is if this term, our h, was itself already 0. So this means our mean curvature must equal 0.